Okay, today I think I'm gonna call this lecture Improper Integrals Part 2. Suppose we want to see if this integral converges. It is the integral from 1 to infinity e to the minus x squared dx. This is a non-elementary integral, so we can't find an exact value for it, but we're still going to be able to determine whether it converges or not by using the comparison test. For x bigger than or equals to 1, x squared is bigger than or equals to x, and therefore e to the x squared is bigger than or equals to e to the x, which means that 1 over e to the x squared is less than or equals to 1 over e to the x. In other words, e to the minus x squared is less than or equals to e to the minus x, as long as x is bigger than 1. So this integral from 1 to infinity e to the minus x squared dx is smaller than or equals to this integral from 1 to infinity of e to the minus x. And this last integral converges. This is the limit as b approaches infinity of the integral from 1 to b e to the minus x dx, which becomes the limit as b approaches infinity of e to the minus x negative as x goes from 1 to b, and this is the limit as b approaches infinity of minus e to the minus b plus e to the minus 1, and when you take the limit you get e to the minus 1 or 1 over e, whichever you prefer. But anyway, by the direct comparison test, this integral converges. By the comparison test. So the comparison test says that if you can find another function bigger than that function, and the integral of that bigger function is convergent, then the integral of the smaller function is convergent. As you can see right here, I'm going to take these two functions, and the function y equals e to the minus x squared is that function, and the function e to the minus x is this function, and before 1 the e to the minus x squared is bigger than e to the minus x, but after that the function e to the minus x is bigger than e to the minus x squared. So this is the point 1 e to the minus 1, and so this is sort of like finding the area of the bigger function is bigger than finding the area of the smaller function. This doesn't mean that the integral from 1 to infinity of e to the minus x squared converges to 1 over e. it converges to something smaller than that. We just don't know what it is, but we can still say that it converges. Okay, let's take a look at this problem, and let's see if this integral from 1 to infinity, 1 minus e to the minus x dx, one minus e to the minus x over x dx. This time the the comparison test cannot be used because we have that 1 minus e to the minus x divided by x is smaller than or equals to 1 over x, and then the integral of this from 1 to infinity diverges. But if the bigger integral diverges, that doesn't mean that the smaller integral diverges. So the comparison test cannot be used for this problem. There is another comparison test that is called the limit comparison test. That test says that if you take the two functions, so if you let f of x equals 1 minus e to the minus x divided by x, and g of x equals to a function that behaves the same as g as x approaches infinity, is 1 over x. If you take the limit as x approaches infinity of f over g, which in this case it would be the limit as x approaches infinity of 1 minus e to the minus x divided by x times x over 1, then you really get the limit as x approaches infinity of 1 minus e to the minus x, and that limit is equals to 1. Because this is bigger than 0, the limit comparison test says that because this function, the integral of 1 over x from 1 to infinity, diverges, then the original integral 1 minus e to the minus x divided by x diverges as well by the limit comparison test. Okay, we're gonna do one more problem where we show that, let's see, I don't know if I did it or not, maybe yes, maybe not, to see if we're gonna use the limit comparison test to determine whether an integral converges or not. So this is the integral from 1 to infinity of 1 divided by 1 plus x squared. And so by the limit comparison test, all we need the two functions f of x, which is 1 over 1 plus x squared, and we're going to take g of x to be 1 over x squared, and we just need the two functions to be continuous and positive from 1 to infinity, and these two functions are continuous and positive from 1 to infinity. And the limit as x approaches infinity of f over g is equals to 1 over 1 plus x squared, the limit as x approaches infinity, times x squared over 1, and this is just, this limit right here is just 1. So because it's bigger than 0, the limit comparison test says that since the integral from 1 to infinity of 1 over x squared converges, and it actually converges to 1 because this is a p integral, which is if p is bigger than 1, in this case p is equal to 2, then this is 1 divided by p minus 1, so 2 minus 1, 1 divided by 1, which is 1. So this is the integral of 1 over x squared. So since this converges, then the integral from 1 to infinity of 1 over 1 plus x squared dx converges as well. but not necessarily to 1. In fact, the limit comparison test says that it converges, but it doesn't tell us what it converges to. However, this particular example, the integral from 1 to infinity, 1 over 1 plus x squared, doesn't really need any comparison test. You can just evaluate the integral. This is the limit as b approaches infinity, the integral from 1 to b, 1 over 1 plus x squared, and this is equals the limit as b approaches infinity, tangent inverse as x goes from 1 to b, and this is the limit as b approaches infinity, tangent inverse of b minus tangent inverse of 1, and the limit of tangent inverse of b at b goes to infinity is pi over 2, and tangent inverse of 1 is pi over 4. So this pi over 4, and all of this is pi over 4. This is what the original integral converges, and we don't really need the limit comparison test. And the reason I did it both ways is so you can see that they both converge, but they don't necessarily converge to the same number. This one converges to 1 and this other one to pi over 4. Okay, it turns out that for this particular function integral, the direct comparison test can also be used, but I'm just going to go ahead and leave it at that. Thank you very much. This is Improper Integrals Part 2.